All right. Hello, everyone. Welcome to your Math 283 review for Professor Kelly. So no one is currently in this meeting, so I'm just going to be talking to you folks watching this later on YouTube. So this is the review material that I received, and I'll just be going through all of them from top to bottom. Hopefully I can finish all of them, but I might not be able to. There's quite a few problems on here. 20, 30 potentially. Yeah, 32 problems. Oh, these are solutions page, sorry. Yeah, there's 32 problems, and yeah, I might not be able to get through them all, but I'll try to get through as much as I can. So let's just jump right into it, okay? So question one is, sorry about that. Question one, just your basic operations you perform on vectors. So we have the magnitude of A, which is just the square root of each of these components squared. So 2 squared plus a negative 1 squared plus 3 squared. That becomes the square root of 4 plus 1 plus 9, which simplifies to the square root of 14. That's your answer there. For B, we have adding two vectors as well as scaling a vector by a constant. So all that is, when you add two vectors, your result is a vector. And then you just go ahead and form this sort of operation. Let's write it like this. So let's first write the A vector. We don't do anything there. Let's first multiply this 2 into this B vector, or scale it by a factor of 2. So all you need to do is multiply each component by 2 right here, these components. So 2 times 2 is 4, 2 times 3 is 6, and 2 times negative 4 is negative 8. Now we have two vectors. We just go ahead and add their components. So 2 plus 4 is 6, negative 1 plus 6 is 5, and 3 plus negative 8 is negative 5. And that is our answer there. For C, dot product, all we do for dot products is take the sum of the components multiplied to each other. So what I mean by that is we go ahead and we multiply the x components together, add that with the multiplication of the y components, and add that with the product of the z components. So all that is, again, is the x component of A, which is 2, times the x component of B, which is 2, plus the x component of A, which is negative 1, times the x component, the y component of A is negative 1, the y component of B is 3, plus the z component of A, which is 3, and the z component of B is negative 4. And then you simplify. So 2 times 2 is 4, negative 1 times 3 is negative 3, and 3 times negative 4 is negative 12. 4 minus 3 minus 12, that is negative 11. Right? And lastly, we have cross products. The cross product, if you remember, whenever you take the cross product of two vectors, your answer is another vector, compared to if you take the dot product of two vectors, you get a scalar, or just a single number value, right? So whenever you take the, if you know how to take the cross products just based off of like what position multiplies to what, by all means, you can do that. I'm going to be showing the determinant definition. So the cross product is the determinants of I hat, j hat, k hat of this matrix with the unit vector. Then we have the values for A, 2, negative 1, 3, and the values for B, 2, 3, negative 4. And all we need to do is solve this determinant. So we go ahead and take I hat. We're going to be doing cofactor multiplication, I think it's called, using the first row. So I hat times the determinant of this 2 by 2 submatrix. So negative 1 times negative 4. Let me just go ahead and write everything. Yeah, negative 1 times negative 4 minus 3 times 3. That'll be times I. And then remember that when you're doing the determinant of a matrix, you have to remember the plus sign, the plus and minus rules. So this is plus, j will be minus. So minus j hat times this submatrix. So 2 and negative 4 and minus 3 times 2. So 2 times -4 minus 3 times 2. And then lastly, we're going to add k hat. Take the determinant of that submatrix, 2 times 3 minus -1 times 2. Right? And that right there, if we just go ahead and simplify that further, we get -1 times -4 is 4. So let me go ahead and write this. I hat times -1 times -4 is 4. So here's 4. This is -9. So 4 minus 9 is -5. Let me go ahead and write it this way. We got -5 I hat. And then we got the minus j hat, and then all this stuff. So let's first simplify in the parentheses. 2 times -4 is -8, minus 6, so that'll be -14. So this will be -j times -14. So the negatives multiply, so it'll become +14j hat. And then lastly, we've got 6 minus, let's see, -1 times -2 is -2. So -2 is +2. So this is going to be a +3 k hat. And you can keep your answer in this form, or if you like writing it in vector form, it's -5, 14, and 3. I'm going to double check with the answers. And oh, -5, 14, and 8. I did something wrong here. 6. Oh yeah, this is 6 plus 2. Sorry, what was I doing? 6 plus 2 is 8. Yeah, oh yeah. So those are the answers there. Okay, and let me go ahead and make some space. Let me just go ahead and write the answer over here, actually. -5, 14, and 8. All right, now let's go ahead and do number 2. Make some space. Okay, number 2. Find the parametric equations for the line that passes through this point that is perpendicular to this plane, and then later find where this line intersects with the xc plane. Okay, so first things first, we got to find the equations for the line. So we know that it's perpendicular to this plane. So if you guys remember your components for equations of a plane, the equation of a plane, this part right here actually contains information. This, the coefficients in front of the variables, so in front of x is 1, -3, and 1, those actually form the normal vector that is that indicates the plane itself. So the normal vector of the plane is just, again, the coefficients in front of the variables. That's 1, -3, and 1. Now, you might be asking, why do we need this? Well, if we're trying to find a line that is perpendicular to a plane, well, if we sort of think of it graphically, we have this plane, we have this as the normal vector. Well, we want a line that is also a line that is also perpendicular to the plane. So we want a line, let's just say the line is like this. We want a line that sort of is parallel to the normal vector. Or in other words, we want a line in the same direction as the normal vector. So if you remember your components for a line, your components for a line, you're going to need a direction vector, which we'll say is v, right? Your direction vector v in this case has to be in the same direction as the normal vector. So all we'll do is we'll set the normal vector 1, -3, 1 to the direction vector v. And now, since we have a v, which is, again, our direction vector for a line, we can go ahead and create the equation of a line. L is equal to, so if you remember your parametric form, it's x is equal to x naught plus v1t, y is equal to y naught plus v2t, and z is equal to z naught plus z2t, z3t, x naught, y naught, z naught, that's just any point on the line. So that's what this will be. And for v1, v2, vt, oh, sorry, this is supposed to be v. that's just the components of your direction vector, right? So if we go ahead and actually write this down now, we'll have the equation, the parametric equations for the line L is x is equal to x naught, which is the point again, 1, 3, 5. So that's 1 plus v naught, v1, which is the x part of this vector, which is 1 times t. So just t. Following the same process, we have y naught is 3, v2 is -3, so minus 3t. And z is equal to z naught, which is 5, plus v3t. v3 is 1, so that's just plus t. So this right here is your parametric equations for your line. Now, in order to find where the coordinates for where this line intersects the xz plane, you have to remember that the xz plane the xz plane, if we sort of draw this, xyz, the xz plane is right here. Well, how do you represent that algebraically? All that is the xz plane. I did that wrong. The xz plane is simply where y is equal to 0. Right? So since you have no y is, and you want to find the point where this line intersects, you just plug in y equals 0 into your parametric equation. So you'll get this deal. Actually, no, it's not like that. So we know what y is equal to. So y is equal to 0. So which is equal to the parametric equation 3 minus 3t. If you solve for t, t becomes 1. So that means that the point at which the line intersects the xz plane is at a t equals 1. So if you go ahead and plug that into all the other equations, you'll get the point, plugging in 1 here, that's x equals to 2. We know y is equal to 0, and z is equal to 6. So this is where the point of intersection with the xz plane occurs. 2, 0, 6, and that matches the answer sheet, I believe. All right. Very straightforward, hopefully. Now we're quickly looking at question 3. What is, if you're given the dot products of a vector on itself, you should be able to find the magnitude, because this is the equality right here. A dot A is equal to the magnitude of A squared. Or in other words, the square roots of A dot A is equal to the magnitude of A. And so in this case, the magnitude of A is just the square root of 36, which is equal to 6. All right. Yeah, that's all it is. Question 4, determine if the following pairs of vectors are orthogonal, parallel, or neither. Well, our test for this is very simple. You know if a pair of vectors are parallel when you take the dot product. If the dot products between, if the dot products between two vectors is equal to 0, I believe, then that means it is parallel, if I'm remembering this correctly. Let me go ahead and double check. But yeah, I'm pretty sure that's correct. Let's just check the solutions, why don't we? 3. I'm mixing it up. Sorry, the dot products, if the dot products between two vectors is 0, then that means it's not parallel, it's orthogonal. That's right. Okay. So we know it's orthogonal when A dot B is equal to 0. We know it's parallel. We know it's parallel if one of the vectors is a scalar of another vector. So you can, if you can sort of think of it that way. And it's neither if the dot product, if neither of these are true, right? So taking a look at all this, we have the vector, I'm going to write in vector form, 1, -3, and 1. And then we also have this vector 2, 2, and 4. So if we go ahead and take the dot product of this, we get 2 minus 6 plus 4, which is equal to 0. So since the dot product of these two vectors equals to 0, we know that A is orthogonal. And now if we do B, we have, let's take the dot product between these two. The dot product is equal to -8 times 6 is -48. 12 times negative 9 is negative 108. And then 4 times negative 3 is negative 12. This does not equal 0, clearly, right? Some very large negative number. So if we go ahead and we know it's not orthogonal, we have to check if it's parallel now. So in order to check if it's parallel, we can go ahead and see, do these have sort of, are these a multiple of each other, right? So let's see what, I think these are actually, but that's the better test, yes. So that's what I thought. You can tell when it's parallel if you can recognize that if one of these vectors is a scalar of the other, or another more solid method, if the cross products between these two vectors is equal to 0, then you go ahead and have your thing. So real quick, let me make sure that this is sharing the right screen now. I did something. Yeah, this is sharing the right screen, I believe. Right. Yeah, okay. Yeah, so in order to find if it's parallel, you simply need to check if the cross product is 0. So we know it's not orthogonal because the dot product's not 0. So if you quickly if you were to go ahead and do the cross products, that's this whole thing again, right? Negative 8, 12, 4, 6, negative 9, negative 3. You should get, let's see, 12 times negative 3 is 12 times negative 3 is negative 36, minus negative 9 times 4, that's negative 36 again. So minus negative is plus 36, so that's going to be 0. We do j, so negative 8 times negative 3 is 24. So it's going to get the negative, though. If to multiply this whole thing by negative, so it'll be 24 minus 24, which is going to be 0. So this comes to 0. And the last part is negative 8 times 9 is 72. So negative 8 times negative 9 is 72. Minus 6 times 12, which is 72, which is also equal to 0. So since this whole thing comes out to be 0, the vector is 0, 0, 0, or the 0 vector, then you know that these two lines are parallel. All right, sorry, these two vectors. And lastly, we go ahead and test both of these cases for this last problem. If we go ahead and take the dot product between these, we'd realize that the dot product is 12 minus 5 minus 10, which is not equal to 0. So we'll give you some negative number. So since it's not equal to 0, it's not orthogonal. If you go ahead and take the cross product of these two vectors, as long as we find a single value that isn't 0, we can stop. So if we take the I hat, that's 5 times 5 is 25 minus negative 1 times negative 2. So that's minus 2. And that right there, that's not equal to 0. So you can immediately stop right there because neither the dot product or the cross product is equal to 0. This is neither. Right? Very straightforward. Just testing your dot product and cross products, right? Number 5, find the scalar and vector projections of these two vectors. Scalar and vectors, okay, of u onto v. Okay, so what they want is the projection of u onto v. So the scalar projection, if it's written like this, if you remember, the components of u onto v, so v is your subscript, which is simply just the dot product of v and u, v dot u, all over v, the magnitude of v, right? It's a little running out of space. Let me see if I can zoom in a bit. There we are. Should be able to, there we are. Yeah, so it's the dot product of the two vectors over the magnitude of this smaller vector v, what you're taking the projection onto, right? So then if we go ahead and do that, v dot u is, let's see, well, 4 times 3 is 12. 12, 7 times -1 is -7, and then -4 times 1 is -4. Right? And then this is all over the magnitude of V, which is going to be the square root of each component squared. So that's 3 squared is 9, plus 1 plus 1. So this is actually 12 minus 7 minus 4. That's 12 minus 11. So this is 1 over the square root of 9 plus 1 plus 1 is 11. And that right there is an answer you can take. This is the scalar projection, or the component of U onto V. Now we're going to take the actual vector projection, which is written like this. The projection of U onto V, same sort of setup. It's going to be the exact same thing, except it's the components of U onto V. So it's this formula right here times the unit vector of V. So you can sort of think of it like this: the components of U onto V times the unit vector of V. So you're going to take the vector V and divide it by its magnitude. It can also be written like this. You might have the formula like this instead, where you have V dot U over the magnitude of V squared. You might see it like that. And then all of this is times vector V. These are all the same formula, but to make it sort of simpler for us, if we go ahead and we can use the first definition we have, where we use the component times the unit vector of V, right? So we know the component of U onto V is 1 over root 11. So we just need to multiply it by the unit vector of V. So we have V's right here. So let's just go ahead and write V there. 3, -1, and 1, all over the magnitude of V, right? And we know that the magnitude of V was square root 11. So if we go ahead and simplify this together, it's the vector V over root 11 times root 11 is 11. And if you go ahead and divide that in, you simply get that this vector is 3 over 11, -1 over 11, and 1 over 11. Right? Very straightforward. Just making sure you remember the formulas. All right, now let's take a look at number 6. Find parametric equations to the line at these 2 points. Parametric equations for the line segment from P to Q. Yeah, okay, so if we remember what the equation of a line requires, you're going to need your direction vector V. And your direction vector V, in this case, since we have 2 points, we can just take the vector from P to Q, right? So if we do the vector P to Q, that's going to be, let's see, 5 minus 2 is 3. -3 minus 1 is -4, -2 minus 1 is -3. And this is our direction vector V. And if we remember, now we can go ahead and set up the parametric equation. It'll be x is equal to, again, we just need a point on the line, so we can pick either one. I'm going to pick P as my x naught, y naught, z naught. You can also do Q if you want. It'll give you the same answer. So if I go ahead and use P, this will be 2. Well, it'll give you a similar answer. They'll both represent the same line, okay? So the x is equal to 2. What am I doing? X is equal to 2, and then V1 is 3. So this will be 3t. Y is equal to 1 minus 4t. And I'm going to write it over here because I don't have space. Z is equal to 1 minus 3t, right? And that right there is your parametric equations for the line. But notice what the question's asking. It's asking for the line segment from P to Q. That means we actually have to restrict the t domain, right? So we have to know what value of t gives you P and what value of t gives you Q. Well, actually, whatever point you pick as your x naught, y naught, z naught as your initial point, that will be t0. So P is actually going to be is equal to t0. And if we look at the equation, in order to get Q, well, it's just going to be, if we solve for that, 5 is equal to 2 plus 3t negative 3 is equal to 1 minus 4t, and negative 2 is equal to 1 minus 3t. All of these come out to the same answer of t equaling 1. So we know that t has to go from 0 to 1. So our domain restriction, don't forget to write this, is 0 less than equal to t less than equal to 1. That's your sort of restriction on the domain of t, which makes a line into a line segment, right? So the main thing to remember there is if you have 2 points, you can easily find the direction vector, create your parametric equations. The more important part actually is if it's a line segment, don't forget to restrict t. Figure out the t values for p and the t values for q, right? Okay, so if we go to 7 now, we're doing the area of a parallelogram. Well, there's a formula for this. The area of a parallelogram spanned by any 2 vectors is simply the magnitude of the cross products, right? The magnitude of the cross products. So first we got to take the cross products. Let's go ahead and do that first. Let's take the cross product of u cross v. So u cross v is equal to this whole deal again. See 1, 1, 2, and this is 3, negative 1, 1. And then if we go ahead and do this now, we'll get 1 times 1. So 1 minus negative 2, so that's 1 plus 2. And then j, we'll have negative parentheses 1 minus 6. So that's there. And then k is 1 times negative 1 is negative 1 minus 3. So we go ahead and simplify this. We'll get the vector 3. This is 1 minus 6 is negative 5. So negative negative 5 is positive 5. And then we have negative 4 here. So that is our cross product. Now we just need to take the magnitude of this whole thing. So the magnitude of this vector is equal to the square root of 3 squared, which is 9. 5 squared is 25. Negative 4 squared is 16. If we go ahead and simplify that further, we should get, let's see, this is going to add up to, what is 9? 9 plus 16 is 25. So this is square root 50, which can be simplified to 5 root 2, I believe. Yes, because this is the same as 25 times 2. So then that's how I got this, right? So, oh, square root 50 from looks of it on your answer sheet is also a valid answer. You can just keep it as that. Okay. So this is, again, just a formula you need to know. Magnitude of the cross product for the area of a parallelogram, okay? Looking at question 8 now, we have 3 vectors, A, B, C. What are we looking at? Find the volume of the parallel pipette determined by A, B, and C. Now, if I remember this correctly, this is this triple scalar product formula, if that's what it's called. It is going to be the dot product with the cross products. So it's A dot B cross C, right? So this will, if you sort of remember your operations, this will be done first, I believe. Well, actually, yeah. So B cross C has to be done first. The cross product has to be done first. And then the cross product gives you a vector. So you'll have a vector times a vector dotted with a vector. So you'll get a scalar. That'll be the volume, right? So volume is equal to this. So all we need to do first, let's take it part by part. What is B cross C? B cross C is equal to, what do we have here? So first let's do I hat, J hat, K hat. Don't forget that for B and C, we want the coefficients. So the I hat of B is non-existent, so that's 0. J hat is positive 1, K hat is positive 1. And then for C, it's 1, 1, 1, right? So now we go ahead and take the cross product of these. So we'll get 1 times 1 minus 1 is 0. For J, we'll get negative 0 minus 1, which is negative 1. So that'll be positive 1 there. For K is 0 minus 1, which is negative 1. So you'll get your final vector of 0, positive 1, and negative 1. With that, we go ahead and take that and dot it with A. A is 1, 1, 0. So dot that with 0, 1, -1. And this is an easy dot product because some zeros and ones in here. All this simplifies out to, so the volume is equal to this, which is 1 times 0 is 0, 1 times 1 is 1, 0 times -1 is 0. So your final answer is the volume is equal to 1, right? So again, this is just a formula with cross products and dot products involved. You just got to remember the formula. And it's just a plug-in check from there. Question 9, find a vector that is normal to the plane. Okay, well, if we just want to find the vector normal to the plane, we just need to find the normal vector of the plane. And in order to do that, we want all the variables on one side and all the constant terms on the other side. So we're going to rewrite this equation as 2x plus 3 minus z, 2x plus 3y minus z. We're going to move the 4 to the other side, so it'll be -4. And then because we can write it as this, the normal vector is simply the variables and the coefficients in front of the variables, right? So it'll be 2, 3, and -1. That is a normal vector to the plane. Very straightforward, right? Question 10, find the unit vector that has the same direction as the vector this. Okay, so in order to find the unit vector with the same direction, all you need to do is, let's just say that this is a vector v. You take the unit vector u is equal to the vector v divided by its magnitude, right? That's the equation to get the unit vector, and that will be in the same direction. So we just need to go ahead and find what is the magnitude of v. Well, let's see, it's the square root of each of the components squared. So 6 squared is 36, 2 squared is 4, and -3 squared is 9. Let's see what this all adds up to. So we got 36 plus 4 is 40, so this is the square root of 49, which is equal to 7, right? So our unit vector is going to be the vector v, which is 6, 2, -3, all over the magnitude, which is 7. So if we go ahead and factor the 1 over 7 in, we get 6 divided by 7, 2 divided by 7, and -3 divided by 7, right? And that's your answer. Looking at number 11, P and Q are these 2 points. Find the vector equation of the line through P and Q, and find the parametric equations for the line. So they want the vector equation and the parametric equation. So those are they're all related to each other. And notice how it says the line through P and Q, the line, not the line segment. So we don't need to restrict the domain, we just need an equation. All right, so the line, if we go ahead and we know that a line needs a direction vector v, which is going to be simply just the vector pq. So let's see, 2 minus 1 is 1, 2 minus -5. Hey, let me write that down. 2 minus 1, 2 minus -5, and 3 minus 2. This is equal to 1, 7, 1. That's our direction vector. And now the vector equation is, it follows the same format. It's the parametric equation, but in a vector, right? So your vector, let's let it be r of t, is equal to x naught, which is just a point. Let's let it be p. So x naught is 1 and plus v1t. So v1 is 1, so plus t. And then y naught, which is -5, plus v2, which is 7t. And then lastly, z naught, which is 2, plus 1t, right? So again, x naught, y naught, z naught, I just picked the point p. You can pick the point q. It's the same line, right? So this is the vector equation form. If you want it in parametric equation, it's just this. Let L let L be the r of t, which is equal to this. X is equal to 1 plus t, y is equal to -5 plus 7t, and z is equal to 2 plus t. Oops. Right, very straightforward. Yeah. Oh, I just realized I'm looking at the answer sheet. In order to the formal equation to find the vector equation is r of t is equal to some points. So your initial point, I think that's the formula. It might be, the variable might be different actually. But this is just going to be a point in a vector. So it's a point. In this case, we're going to use P. And then you add it to your direction vector times T, right? So in this case, you pick a point. I'm going to pick this point, and then your direction vector V is your direction vector we calculated here, right? So the reason why we picked P again is because we did the vector PQ. If you did QP, I think you have to do Q as your direction vector. Sorry, as your point. I might be wrong about that. But yeah, you guys understand the process. We've done this a few times already in this review. So that's all it is. Question 12. Find an equation of the plane through these points. So an equation of a plane needs the normal vector, and it also needs the a point on the plane itself, right? So in this case, we have points. We just need to find the normal vector. So in order to find the normal vector, we can, so let's sort of let this be P, let this be Q, and let this be R. And in order to find the normal vector, if we just need to create some vectors that are on the plane and then take the cross product of that, right? So if we sort of think of it graphically, we have a plane. Here's point P, here's point Q, here's point R. We want to find the normal vector. Well, can I not just say this is a vector, this is a vector, and if we take the cross product, remember that the cross product will give you the normal vector, right? So the normal vector is going to be the cross product of P and Q, P vector, the vector PQ cross with the vector PR. And again, this will give you the same normal vector if you do any combination of P, Q, and R. It just might be the negative version. So it's not that big of a deal though. So we're going to find the normal vector is we're going to let it be the cross product of PQ and PR. So what are those vectors, first of all? Well, PQ is, let's see, -1 minus 2 is -3, 1 minus 1 is 0, 1 minus 3 is -2, crossed with 3 minus 2 is 1, -6 minus 1 is -7, 7 minus 3 is 4. And that is our two vectors. Now we're going to cross that. So let's go ahead and take the determinant, I, J, K, hat, let's see, -3, 0, -2, 1, -7, 4. What does that equal to? Well, it will be, that's 0 minus -7 times -2 is +9, so -9. So 0 minus 9 is -9. So we -3 times 4 is -12. -12 minus -2, it's -12 plus 2, so it'll be -10. So we cancel out later. And then K is -3 times -7, that's 21, minus 0, so this is 21. So let's simplify the sign. So rather than be -10, it'll be +10, right? Let me just write this smaller. So this is +10, this is 21, I believe I said earlier. Yeah. And now that we have this, let's see if I'm just double checking the answer sheet real quick, making sure I did my algebra correctly. PQ, PR, cross products. Oh no, I did the first part wrong. Wait a minute. They did PQ and PR as well. How to get -14? Give me 1 second. So yeah, so instead of -9, they got, oh yeah, why did I added that? Sorry. Yeah, this is not supposed to be -9, it's supposed to be -14 because 0 times 4 is 0. So 0 minus -7 times -2 is +14. So 0 minus 14 is -14. That's why I went wrong. Yeah, -14, 10, 21 is your normal vector. And now that we have the normal vector, we can go ahead and just plug it into this form, right? So the equation of plane will be v1 times x minus x naught plus v2 times y minus y naught plus v3, oh sorry, n. These are not supposed to be v's, these are n's because this is the normal vector, right? So n1, n2, n3 times z minus c naught. This is all equal to 0. And then if we plug everything in, so we'll have -14 times x. Let's let the point P be our x naught. So x minus 2 plus 10 times y minus 1, and then plus 21 times z plus 3, right? Oh, actually, yeah, okay, well, I'll go ahead and go along with this, but there's actually a way easier point we could have done. If we did point Q, where it's -1, 1, and 1, you'll get a plane that is a lot easier to write. But I'm already writing this, so let's just go ahead and finish it up. This is equal to 0. So if you use any of these points, it'll still be correct, just so you know. But I should have done point Q because it'll make the math a lot easier. So let's just go ahead and finish this up, though. So we'll get -14x plus 28 plus 10y minus 10 plus 21z minus 63 is equal to 0. Simplify it out, what do you get? -14x plus 10y plus 21z is, oh, and you could actually keep it in that form. Oh, but this whole thing actually simplifies out to 45. No, I'm pretty sure, yeah, I'm pretty sure if you picked this point as well, it should give you the same answer, but the answer sheet picked point P, so the first point, and this is the answers. So your professor is actually okay with accepting this line right here as an answer, which I would just keep it like that so you don't have to simplify or waste time, right? But yeah, this is the equation of the plane using point P. You'll get a slightly different answer. This number at the right side will be slightly different if you use any of the other points, but it'll still be the correct answer. Okay, so don't shy away from using easier points. Like point Q is what I should have used, in my opinion, because it's faster, in terms of algebra. But they're all valid answers. Okay, the formula, the solution sheets uses point P though. Anyways, let's look at question 13 now. Two planes, we got x plus y plus z equals 1. Okay, and they intersect on a line L. Find the point on this line that has the x coordinate 0. Okay. Find a vector which is parallel to L. Okay, so if I'm thinking of this correctly, all we need to do in order to find, for question 13, to do part A, to find a point on this line that has the coordinate 0, you just go ahead, x coordinate 0, you just plug that into both equations. X is equal to 0. The first equation gives you y plus z is equal to 1. And the second equation will give you -2y plus 3z is equal to 1. And now you have a system of linear equations with two variables. You can pick your method to solve it. So for example, you could solve for one variable and plug it into the other. You could do elimination, substitution, however you want. Coincidentally, because these are both equal to 1, you could just set them equal to each other. But when you do the math, so what I mean by that is, like, for example, let's say I want to solve for y here. Y is equal to 1 minus z. I can plug that in here. Let's see what we'll get. -2 times 1 minus z plus 3z is equal to 1. If we simplify this out, we'll get -2 plus 2z plus 3z is equal to 1. So we'll get 5z is equal to 3. So z is equal to 3/5, right? And if you plug it back into this equation right here, y equals 1z, y has to be equal to 2/5. So that's how you can potentially solve it. Pick your method. They all should give you the same answer in the end. So this is your x equals 0, y is equal to 2/5, z is equal to that. So the point for part A is 0, 2/5, 3/5. Right? So now we have a point on the line. So perfect. Find a vector v which is parallel to this line. Okay. So in order to find that, well, in order to find the vector v which is parallel to the line, or the direction vector of L, we have to first figure out where can we get two vectors that would give it to us. Well, if you remember, planes have vectors embedded in them, which is their normal vector, right? So if we think of it geometrically, let's first sort of sketch a vector like this. Here's the line L, and then let's say that here's another plane, right? So you imagine it like that. This line is L, and then we have plane 1, plane 2. Well, if we remember, each of these planes has a normal vector to them, right? So here's the normal vector N1, and here's the normal vector N2. Now, if we want to find the vector that is which is parallel to L, or the direction vector of L, actually, we have to use two vectors. And in order to get that, if you sort of think of it geometrically, that vector right there that is in the direction of L, let's just go ahead and let's say it's this way, vector V. Vector V is simply going to be the cross product of the two normal vectors. Okay, so let's write that down. Vector V is the cross product of normal vector 1 and normal vector 2. So in order to do that, you just take the cross product of n1 and n2. What is n1 and n2? Well, it's the coefficients in front of each of the planes, right? So n1 would be 1, 1, 1, crossed with n2, which is 1, -2, 3, right? And then if you actually go ahead and do that, I'm going to go ahead and skip the algebra for this. It's again a cross product. You guys know how the process works. This will give you the answer, the vector 5, -2, -3. Yeah, 5, -2, -3. That right there is the vector parallel to L. And now in order to write the set of parametric equations for the line L, we have the direction vector V, which is parallel to L. If it's a vector parallel to L, that just means it's a direction vector, V. And we also have a point on the line right here, 0, 2/5, 3/5. So since we have a point and the direction vector, we can easily create the equation of the line. So the parametric equation of the line is equal to x is equal to, we'll use this as x naught, right? So 0 plus 5t, so this will just be 5t. Y is equal to 2/5 minus 2t, and z is equal to 3/5 plus 3t, right? And that right there is our parametric form. Very straightforward, hopefully. It's just remembering these little nuances, like if you have two planes that intersect, that the vector that is parallel to that line is just the cross product of the normal vectors. That's probably the biggest thing to remember to solve this problem. Cross product of the normal vectors of two planes that intersect will give you the direction vector of the line. All right. Question 14, find the unit vector orthogonal to both of these planes. Unit vector orthogonal to both of these planes. Okay. So, well, how do we find orthogonal vectors, right? So in order to, am I thinking this correctly? Find the unit vector orthogonal. So let me just refer to the answer sheet if I'm understanding this correctly. Okay, yeah, I am thinking this correctly. Yeah, so it follows a similar process as we did in the previous problem. So again, you can find the vector orthogonal to both planes by, I believe, it's taking the, oh, these aren't planes. Oh, no wonder I'm confusing myself. I was like, how does that work? These are just vectors themselves. So this is a, let's just let this be v1. Let's let this be v2. Well, in order to find the orthogonal, first think of what is an orthogonal vector. So the orthogonal vector v, let's do that. The vector perpendicular to both of these vectors is simply just the cross product, right? And in order to find the unit vector, you simply take the orthogonal vector, if I can write it correctly, the orthogonal vector, and divide it by its own magnitude, right? So if you were to quickly do that, if you refer to the, if you go ahead and actually compute that, so taking the cross product of these two vectors, you should get 5, -1, 8, and then if you take the magnitude of this, it should be √90. So then your unit vector u is equal to 5 over √90, -1 over √90, and 8 over √90. So I'm sort of starting to skip some of the algebraic steps because we sort of covered the process of cross products several times already. So hopefully you've got enough practice on that. If you want to give more practice, go ahead and compute that yourself. Double check with the solution sheet. Okay. Question 15, find parametric equations for the curve of intersection of the parabolic cylinder, z is equal to 3y squared, and the plane. Okay, so we want to find the curve of intersection. Okay. Oopsies, I'm gonna go ahead and. So in order to do this, I believe all we need to do is simply plug it in, right? So okay. Yeah, so in order to find the curve of intersection, what you want to do is you want to make sure that, okay, let's remember this. We want a curve, so r of t, that'll be in terms of this. So the x component is in t, in terms of t, the y component's in terms of t, and the z component's also in terms of t, right? So in order to do that, what we usually do, there's technically infinitely many solutions to this, I believe. So all you need to do is just, the sort of thought process we go through is pick your variable and let that be t. Set that variable equal to t. So for example, we can set x equal to t, or we can set y equal to t, or z equal to t, and then from there solve everything else out, right? So in this case, to make our life easier, we're given a parabolic cylinder where there's only one variable left, right? So z is in terms of a single variable. In this case, that single variable is y. So to make our life easier, which we'll see later, we're going to let y equal to t, okay? So if we're going to let y equal to t, what does that mean for everything else? Well, let's plug it into this equation. So that means if y is equal to t, then z is equal to 3t squared, right? And now how do we, that's already two parts right here of the curve. Now we need to find what x is equal to. Well, right here, we have an equation of the plane that has the x that we need. So it'll be x plus y. Well, we already said y is equal to t, so plus t. And z, what is z equal to? Z equals to 3t squared. So it'll be plus 3t squared. This is all equal to 1. So if we solve for x, we get this. X is equal to negative 3t squared minus t plus 1. And that right there is your x component. Now, if you just plug that all into the space curve, that means r of t is simply equal to this quadratic equation, comma, t, comma, 3t squared, right? And that is your answer if you start off with let y equal to t. Now, again, the other trivial methods that you can go through is you can set x equal to t, you can set z equal to t, and then work through the process that way and find your x, y, and z. Either way, well, you might get a slightly different answer, but as long as you do the algebra correctly, it should be correct. Because again, there are many, many, many different answers to this question. It's just pick the method that you find to recognize the best. If you want, you could. I believe you can do all of these types of problems, like these curve of intersection. You can solve all of them if you just set x is equal to t, I think, and then from there work your way out. It's just some of these equations will not be as pretty. So first, try to analyze the equations you're given. Look at the curves. Look at the surfaces you're given. And then see if one would be easier to set equal to t first, right? So, for example, if you're ever given a surface, or like for example, parabolic cylinder, or just any z is equal to anything in terms of just one variable, let that variable right here, so in this case y squared y, let that variable be t. It'll make everything else easier. Well, everything else look nicer. It tends to be that way anyway. So again, in the solution sheet, they solve it with y equal to t. You can start off with x equals t if you want. You could also start off with z equals t. It's just the answer will be slightly different, okay? So, but as long as you do the algebra correctly, you can go ahead and you should get the right answer regardless. All right, 16. A right answer regardless. There's no the right answer for these types of questions, 15. So in 16, though, we got find an equation of the plane through the points and parallel to this plane. Okay, so this is, again, what do we need for equation of a plane? We need the normal vector and a point. Well, they gave us a point. What is the normal vector? Well, if we want a plane to be parallel to another plane, that just means that their normal vectors are the same. So the normal vector for our plane that we're using is the normal vector of this plane right here, which is going to be 2, -1, -1. right? You can sort of think of it like this graphically. If I have this plane and then I want another plane parallel to it, this has the normal vector n. Well, it just so happens that this parallel plane also has the same normal vector n, right? Because they're both sort of just above the offset of each other. The vector, no matter what the offset is, going to still be the same vector. So the normal vector of the plane you could create is simply the normal vector of this parallel plane. And with that, you have your normal vector, and then you have your points. So you go ahead and follow this formula. The component of the normal vector times x minus this point, plus, oh, this is be minus 1, sorry, minus 1 times y minus 1, and then minus 1 times z plus 1 is equal to 0. And then right there, that's your answer. Right? Very, very straightforward for this one. Just making sure you recognize these properties, like if, between different objects, right? So parallel planes have the same normal vector. That's the takeaway there. 17, find the angle between these two vectors. I believe you have a few options to do this, but probably the easiest formula is the geometric definition of a dot product. The geometric definition is written as this, I believe. So the dot product of A dot B, the geometric definition is the magnitude of A times the magnitude of B cosine theta, and cosine theta being the angle between these two vectors, right? So in order to find the angle, you want to solve for cosine. So cosine theta is equal to the dot product over the product of the magnitudes of each of the vectors. And in order to find theta, you just take the inverse of this, right? So let's go ahead and solve this first. A dot B is, let's see, I'm just going to jump ahead in the answer sheet just to speed things along. A dot B is equal to 5. And then the magnitude is root 26 and root 30. So this actually simplifies out to 5 over root 780. Right? So that's cosine theta is equal to 5 over root 780. So in order to find the angle, we just take the inverse now. So we take the cosine inverse. Theta is equal to cosine inverse of 5 over root 780. And I'm assuming you're allowed a calculator on this exam. So you'll be able to compute this. And in degrees, it's about 79.69 degrees. Right? So key thing here, remember this formula. It's the geometric definition of a dot product. All right. 18. Suppose that A is equal to this. If the component of B on A is that, find the projection of B onto A. Okay, so interesting. Let me think about this for a second. Do we know what B is? Oh yeah, it is. It is just a sorry. I thought I was just double checking with the solution sheet, and I thought there was a typo, but no, I'm just incorrect. Let me just double check with that though. Yeah, I was just overthinking it. Yeah, I was incorrect. Yeah, so if you remember in one of the previous problems, I think, let me just look at the numbers so I can find it. Problem 5, we remember that we can use this formula for projection, the one that involves the components. So the projection of B onto A is actually the components of B onto A times the vector A over the magnitude of A, right? So if we can take advantage of this because we know what the components of B onto A is as a scalar, right? So that makes it a lot easier. And we can quickly calculate what the magnitude is as well. So the component of B onto A is just 7. Vector A is just as it is. And the magnitude of vector A is the square root of 4 plus 4 is 8. So square root of 8, right? And if we go ahead and simplify this whole thing now, what do we get? Well, we get that okay, so the answer sheet simplifies, before we continue, the answer sheet simplifies root 8 to 2 root 2, which is correct, obviously. And then I'm writing on the next problem. So we can simplify root 8 to 2 root 2 times the vector 2, 0, 2. And then if we go ahead and just multiply everything in, you should get 14 divided by 2. 14 divided 2 times 7 is 14. And then 14 divided by 2 is 7. So that's 7 over root 2. This is 0, and this is the same thing, 7 over root 2. Yeah, and that's your answer. So this is taking advantage of this formula we had earlier. Component of B onto A times a unit vector of A, right? Okay, 19. Find the time t in the point where the line, that's our line, intersects the plane. Okay, so we need to find where this line intersects the plane and at what time t. Okay, how do we do this? Oh, well, in order to do this problem, well, look at the variables. We have this space curve in terms of t, and we have this plane in terms of x, y, and z. So if we can sort of take advantage by changing this equation right here, this vector equation, into the parametric form, right? Because we know that if we break it down into its parametric form, we know that x is equal to this component in front of I, which is t. X is equal to t, y is equal to 1 plus t, and z is equal to 1 plus 2t, right? And now that we have the variables x, y, and z, we can plug it into this plane equation. So x is just t. We got 4 times y, which is 1 plus t. And then we got 5 times z, which is 1 plus 2t. And then now we can solve for this. We can solve for the exact time t, right? So if you simplify this all out, you should get t is equal to 2. So that's our time t. And in order to find the point, all you need to do is plug it back into the space curve. So we'll do r at 2, which gives us this vector, which will be our point in a sense, right? It'll give you 2, 3, 5. So the point is 2, 3, 5, right? That's your answer for 19. Definitely the thing to take advantage here. You can change the form of a space curve or vector equation into the other forms. So for example, parametric, and you can use the parametric form, the XYZ equation, and plug it into other equations like equations of planes, for example. All right, 20. Write an equation of a sphere with a center at the point that and a radius of that. So if you remember the equation of a sphere, the general formula is this: x minus, what is the general? Let's just say this is a. Sure, I'm not remembering the normal terminology, so the normal variable choice. Let's let this be b, and let's let this be c. Right? This is all equal to r squared. Very straightforward. As long as you plug it all into this equation, you'll get x plus 5, all that squared, plus y squared, plus z minus 2 squared is all equal to 16. And that right there is perfectly fine as your equation of a sphere. So this is, again, memorizing formulas. So from the looks of it, a lot of this exam will just be making sure you remember a lot of your formulas, how to apply them. And also remembering certain properties and nuances and relations between vectors, between planes, between lines and planes, and all that stuff, okay? So a lot of just plug in. The work is not too difficult in terms of like the actual computation. It's more setting it up. So if you can set up the problem, you should be able to solve the rest of it, right? Okay, 21. Let A equal to this vector, B is equal to this vector. Okay, we're going to find the projections of B onto A and A onto B. So I'm going to go ahead and skip this since that's just, again, computations. You can go ahead and check the answer in the answer key. All right, so we're going to skip that. We'll look at 22. Describe the cross-section / traces of the surface, then identify and sketch the surface. So in order to find the cross-sections, what we tend to do is we sort of set each of these variables one by one as k, and then we sort of change the value for k and see what shapes we see, right? So for example, if we let x is equal to k, and then we make a table of k, and then if we substitute this in real quick, what do we get if we substitute this in? We get 3k squared plus y plus 3z squared. Well, if we solve for y, we'd get y is equal to negative 3z squared minus 3k squared, right? So remember that we're treating k as a constant, right? Some arbitrary constant. So let's say we can do -1, we can do 0, we can do 1, and then so on and so forth. And then we have to look at what's left. So the reason why I arranged it in such a fashion is because y is just to the power of 1. So we can find an equation of y in terms of z, right? So y is equal to something in terms of z. So if we go ahead and now plug in -1 for k, what do we get? Well, we get y is equal to negative 3z squared. And then -1 squared is just 1. So this is -3. If we plug in 0, you just get negative 3z squared. And you plug in 1, you get the same thing as -1. So it's negative 3z squared minus 3, right? So, and then you can keep testing different numbers until you can sort of figure out what's going on here. What is the shape or surface what is the shape that we're seeing? What is the cross section we're seeing? Well, all we're seeing really is y is equal to negative 3z squared. And then the -3 is just an offset. So that's we can sort of think of it as like a shift in the z direction, in the y direction. And all we're seeing really here, this is a parabola. Right, so all these cross sections, if you cut it along the x axis, you'll see that so you're looking at the YZ cross sections, you'll see that you're just getting a bunch of parabolas at slightly different heights, right? And so we know that if we draw, so we sketch this. So let's let this be y, let this be z. Yeah, so what we're getting is like a bunch of parabolas, something like this. So this right here is at k is equal to -1 and 1, because we have this offset at -3. And we also, since it's a negative 3z squared, let me draw it in a more recognizable way. So since the input is z, let's sort of draw it this way. I need space. What am I doing? We know this is a parabola. If I go ahead and let the input be z, so there, and then y is here. So this is like our normal parabola. We have it starts at -3 here, and then it goes downwards, right? And then we also have 1 over here at 0. So this is at k is equal to 0. This is at k is equal to ±1. And then you realize as you increase or decrease, it'll just continuously go down. So it's a bunch of parabolas, right? That's the cross section if you were to cut across the x-axis. So you want to sort of do that sort of process where you set x equal to k. You want to do that for all of the other variables too. So if I set y is equal to k real quick, what do we get? Well, we'll get k, if we make our table again, then what equations are we dealing with? Well, we're actually going to get, if you simplify it out, you'll get 3x squared plus k plus 3z squared, right? Is equal to 0. Well, if you solve, if you realize you have two variables and they're both squared with the same factor, there's actually almost a circle. So if we sort of simplify it like this, 3x squared plus 3z squared is equal to minus k. Well, what do we have? We have, this is an equation of a circle, right? And we actually can divide 3 onto the whole thing. So we'll have negative k over 3. Now we have x squared plus z squared is equal to negative k over 3. Well, x squared, a variable squared plus another variable squared, that's literally an equation of a circle with a radius of radius squared of negative k over 3, right? So because, let's just say, for example, if I plug in, what happens if I plug in 1? If I plug in 1, I get a negative I get x squared plus z squared is equal to -1/3, right? And this is not possible. So because you can't have a circle with a negative radius, right? So what is this saying? And another way you can think of it, a number squared plus a number squared will always be a positive number, so you can't have a negative answer, right? So what is this saying? K in this case has to be greater than, less than or equal to 0, right? Because any positive numbers will mean this is negative, so you want K to be negative. So if we for example just set this equal to 0, we get x squared plus z squared is equal to 0. That's just a radius of 0. So really this is just a single point. So if we sort of graph this, let's just say this is x, this is z, this is right here, that's k equals 0. If we get -1, what is that? We get x squared plus z squared is equal to 1/3. So that's a radius of like something right there. And then if you increase this, let's say -3, you get x squared plus z squared is equal to 1. Now you have a radius of 1, and so on and so forth. So these are just sort of your cross sections. So what is this? What shape is being made if you cut across the y-axis? Well, you get a bunch of circles. And I'm gonna tell you right now, if you go ahead and do z is equal to k, you'd get a bunch of parabolas again, except in a slightly different format. I can't spell parabola. So based off of this information, you're getting a bunch of parabolas and a circle. You're getting 2 different parabola cross sections and a circle cross section. Well, if you sort of think of the surface in the way it's supposed to be, all this is, if we sort of combine all these cross sections together, we'd get, if we do it in the sort of 3D plane. Well, let's first look at this. This is x, this is y, this is z. Well, we know that in the xz direction, there's a bunch of circles here. So there's a, well, that's not where it's supposed to go. We know at the origin, there's nothing going on. At k is equal to -3, so at y is equal to -3, so like about here, we know that there's a circle of radius 1. And then if you get closer to the origin, it's smaller. And if you go farther away, it's bigger, right? And then we also, if we look at the YZ cross section, so we actually get a bunch of, if you technically look at it, so it's this way, you get these bunch of parabola cross sections, right? So let me do that in a different color, actually. You sort of get this sort of cross section, and you get slightly smaller as you go to the sides, right? And then just so in case you were wondering, if you do when z is equal to k, you'd get these cross sections going this way, right? So if you knew from the start what kind of surface this is, then good for you. But if you want to analyze it based off these cross sections and put the cross sections together, you should realize that this is actually simply just a paraboloid. A paraboloid along the negative y-axis, right? So this whole thing is a paraboloid along the negative y-axis, right? Or in other words, in your answer sheet, it says on the XZ plane, right? But they're the same thing. Yeah, so this is the sort of process you'd go about doing it. The cross section, but I know this is definitely like conceptually, sometimes it's a little hard to understand, but you can at least get your points for describing the cross sections by, again, take each variable. We first started with x, set it equal to a constant k, play around with the constant, just change the numbers a bit, and then try to simplify the equation in such a way that you get something that you recognize. So if there's ever a single term variable, set one of them as, write the equation solving for that. So y is in terms of z. We realize that y is in terms of z, some power of z squared, right? That's a parabola. We know that. And when we change k, we just realize it just shifts a bit. And then when we set y equal to k, we'd get 2 variables squared, and we realize that's just a circle with a different radius, right? And if you did z, you'd realize it'd be similar to when we set x equal to k. You get a parabola again. So realizing the different shapes, making these tables, graphing it so you can see the shapes, and more importantly, recognizing what each of these equations represent, you realize that these lines and shapes, these curves rather, if you put them together on the corresponding axes, you'd realize that you can sort of sketch out the actual surface that you're working with based off of the cross section. In this case, the surface is a paraboloid along the negative y-axis, or just the y-axis rather. Paraboloid along the y-axis is perfectly fine. But yeah, that's a sort of process. So we've got about 5 minutes left. I'm going to try to speed through these last bits because I understand that these next bits are just derivatives. So let A equal this, B equal that. Find the derivative of A dot B. If I'm not mistaken, isn't this just going to be, oh no, it's not. Okay, so first, what is A dot B? A dot B is when you take the cross product of this whole thing. What is the cross product? Well, if you take the cross product, you end up getting no, I see. They want you to use the product rule. Okay, so when you have the derivative of the dot product, this is literally, you can sort of remember it as your product rule. You can sort of think of it as a function times a function, right? So you take the derivative of two functions multiplied to each other. If we think of it in terms of back to calculus, the derivative of f of x times g of x is equal to f prime times g plus g prime times f, right? And it's actually followed a similar process for this case right here. So actually, let me rewrite it in a way that is more f times g prime, right? It's actually the same thing in this when you're doing dot products. So the derivative of the dot product is equal to the derivative of the first dotted with the second plus the first dotted with the derivative of the second, right? So a prime dot b plus a dot b prime, that's the formula. And then if you go, then from there, you just go ahead and plug and chug, right? You actually just solve the whole thing. Now, real quick, what is the derivative of a vector? A derivative of a vector. So let's go ahead and, for example, take the derivative of a. So if we want to take the derivative of a, we just take the derivative of each component with respect to t. So the derivative of t squared is 2t. The derivative of e to the t is e to the t, and the derivative of 1 minus t is -1, right? So it's just taking the derivative of each component and going ahead and plugging into this whole thing, right? So I'll go ahead and I'm going to move on from here because that's just simple calculus, calc 2, calc 1 stuff, taking derivatives, right? You should know how to take the derivatives of each of these components, and then the dot product again is just you're multiplying each of the components together. So you can go ahead and check the answer sheet for that. So that's 23. I'm going to skip ahead trying to find good problems to make sure I want to cover. 24. Okay. What is the relationship between position, velocity, and acceleration? Well, your position's t. If the derivative of position, so r prime, the derivative of your position function, if the position's r, the r prime is simply your velocity. So the derivative of position is velocity. The double derivative of r prime is the same as taking the derivative of velocity, which in reality is all just acceleration. So what's your takeaway here? Derivative of position is velocity, derivative of velocity is acceleration, or in other words, the second derivative of position is your acceleration, okay? And follow the same process. Take the derivative of each component, that's all your answer is, okay? This is again following the same deal. That's asking you to sketch the space curve. So this is a two-dimensional thing. I can try to do that real quick. If you're unsure how to sketch this, what you can do is you can sort of just plug in, what's it called? Plug in various t values and then sketch it that way. So this actually ends up being a parabola. Let's offset something like this. And when it asks you to sketch this, you can go ahead and look at the solution sheet to see what happens there. But yeah, the tangent vector is literally just the vector tangent to that specific point, right? So go ahead, play around with that. This is again testing your understanding of derivatives of vectors. So now let's get to what is this? From the unit tangent vector to the vector function. Okay, so the unit tangent vector, so I think it's written as like this, capital T, I think is what it is for unit tangent vector. It's just going to be r prime, so the derivative of your original vector over the magnitude of r prime, I believe. I think that's what the equation is. Let me just double check. Yeah, you take r prime, so that's the tangent vector. Yeah, it is, and I am using the right variables. Yes, so that's all it is. So first, get rid of unit. What is the question asking? Find the tangent vector. So first, in order to find the tangent vector, that's just the derivative of the first vector r. So r prime will give you tangent vectors at a certain point. In order to find the unit tangent vector, you just take the tangent vector and divide it by its magnitude. So yeah, so this is the formula there. It just follows the same idea. Whenever you're taking a unit vector, so you can first find the vector they're asking for, then you should be able to find the unit vector, right? And I'm a little over, but I'm going to quickly cover this. Integrals of vectors, same deal. If you're ever having the integral of a vector, you're just going to be, let's say that v, let's do this. If you're ever taking an integral of a vector function in terms of t, all it is, it's the integral of each individual part, right? So it's the integral of x, the integral of y, the integral of z, all in terms of dt, right? And then in this case, it's a definite integral because you have bounds. So you'll go ahead and integrate to the bounds. But let's say that it was an indefinite integral, so there is no bounds. Don't forget that you'll have a plus c vector. So if you remember in Calc 1 and 2, Calc 1 rather, indefinite integrals, you have a plus c. But in this case, our answer is a vector, so we need a plus c vector, right? But that's only if there's no bounds to your integral. And then I'm going to unfortunately, I am out of time. So I'd go ahead and just make sure you double check these last few problems. The length of a curve is just a formula. L is equal to, what is it? It's the integral from a to b of the magnitude of r prime of t dt. That looks to be what the formula is. Is that my understanding? Yeah, that looks to be the or maybe I'm misunderstanding this. R prime squared, is it? Yeah, it might be the magnitude squared. I double check. This is not I'm not remembering it off the top of my head. So double check in your notes, what is the arc length of the curve? Again, that's just a formula. These are just velocity and acceleration problems. So this is where the indefinite integrals come in, where you have to have your plus c. This will be your some initial value. And then 30 and 31, 32, all that good stuff. Go ahead and just double check what's going on there, right? So this for 30, you're gonna need to, this is just, again, velocity stuff. So derivatives is your position. This one's testing your differentiation rules. So look those over again, please. And lastly is just taking some answers there, right? So yeah, unfortunately, I couldn't get to the very end, but if you check the solution sheet, your professor does a really good job of showing each step and going through the work, so you can always review that way. All right, but yeah, that's all for me. Hopefully you got just some general test taking tips. As you can see for this exam, most of the difficulty comes from remembering the setup. If you can set up the problem, you will most likely be able to solve the algebra from there, right? Because all the algebra is just simple algebra. It's, again, just the difficulty is in the setup and actually setting up the problem. So go over these problems, make sure you understand the concepts of what pieces of, what objects have such an information, like lines have a point and a line. In order to make a line, you need a direction vector and a point. In order to make a plane, you need a normal vector and a point. The relationships between lines and planes, how they intersect, how two planes intersect, how a line and a plane intersects. I think I said that. But yeah, all this good stuff. Definitely the difficulty comes from the setup and all these different formulas. But yeah, I wish you guys good luck on your exam. Don't stay up too late studying. Make sure you eat a proper meal, get a good night's rest, all that good stuff. And yeah, that's all I have for you. If you're watching this at home, just be aware that if you do have any questions before your exam, the Math Center is open online and in person from 9 to 4 p.m. So feel free to give us a visit if you have any questions, all right? But yeah, that's all we have. Well, that's all I have. Thank you guys for watching. See you guys next time.